What's up, AP Physics C Mechanics student? Welcome back to our elegant physics videos. Today's topic, 2.10 circular motion part 3. So let's jump right in. In the previous session, we have introduced two types of acceleration or two new components of acceleration. The centripetal acceleration, which is responsible for the change in the direction, and the magnitude of this kind of acceleration can be calculated via v squared over r. This direction, the direction here is toward the center, it's seeking the center. Now, the second type of acceleration is the tangential acceleration, which is responsible for the change in the speed. And how we can find it? Actually, we have different ways to find it. For example, A is equal, the tangential one, r times alpha. And also we can use the kinematics equation in case the acceleration is constant. So if the acceleration, the tangential is constant, and we can find the tangential acceleration via the set of equations such as v is equal v0 plus at. Actually, this acceleration here, written in this equation, is the tangential acceleration. We can apply delta x is equal v0t plus half at squared. And also we can apply v squared is equal v squared 0 plus 2 tangential acceleration delta x. And finally, the delta x is equal v plus v0 over 2 multiplied by t. But this equation won't help us to find the tangential acceleration, because this equation is totally independent of the tangential acceleration. Another way to find the tangential acceleration is by relying on this equation. But here you need to pay attention because you will need to find the alpha. If the alpha is constant, then you can use the angular terms in this way. So, for example, omega is equal omega 0 plus alpha t. So this equation will help us to find the alpha. After we found the alpha, we just plug it here to get the tangential acceleration. Delta theta is equal omega 0 t plus half alpha t squared. Omega 0 is equal omega 0 squared plus 2 alpha delta theta. And finally, that the delta theta is equal omega plus omega 0 over 2 times t. Now, in circular motion, always and forever, the centripetal acceleration will be existed because we have variation in the direction, and this is what happen always in circular motion. But it's not necessary to have the tangential acceleration because sometimes the speed is constant, so the tangential acceleration in this case, it's going to be 0. So the tangential acceleration at is equal r alpha is due to the variation of the speed. So it's not exist if the speed is constant. The tangential acceleration has direction tangent to the trajectory, and this is very, very important. So always, whenever this kind of acceleration is existed, then the direction of this acceleration will be tangent to the trajectory. So let's do the two cases. In the first case, the object is moving around the circle and is speeding up. And let's assume here in this scenario that the direction of motion is clockwise direction. We're going to consider these points to determine the direction of velocity, tangential acceleration, and centripetal acceleration. In the first point, the direction of the velocity will be always tangent to the path, and it indicates the direction of motion. Since the direction of motion is clockwise, so the direction of velocity will be to the right. The centripetal acceleration is existed here because we are dealing with circular motion, and the direction of the centripetal acceleration will be toward the center. But before that, let me add the velocity vector for the other possible points. So let's assume that the object now is located here. So the direction of the velocity in this way. What about this point? The direction of velocity, sorry, this point, then the direction of velocity is to the left. And finally, for this point, the direction of velocity will be up. What about the centripetal acceleration? In circular motion, the centripetal acceleration always involves, and it's toward the center at different locations. So centripetal acceleration is toward the center, centripetal acceleration toward the center, and then this point and that point. Now, since the object is speeding up, then the tangential acceleration will be always with the same direction of the velocity. And it should be also tangent to the path. So the direction of the tangential acceleration will be this one, and here, and there. And from unit 1, we have learned that if the acceleration and the velocity have the same direction, then the object will speed up. This is why we can find it as in the same direction of the velocity. Now, what will be the direction of the acceleration vector? Remember that the acceleration vector is the vectorial sum of the centripetal plus the tangential. Now, since the centripetal direction is toward the center, the tangent is to the right, then if we complete the rectangular shape, the diagonal here will represent the acceleration vector. Also for here, the diagonal will represent the acceleration vector, and the acceleration vector here is like this and like that for this situation. Now, let's consider the second case where the object is slowing down. So again, remember that the acceleration, the tangential acceleration is r alpha, and this is due to the variation in speed. The tangential acceleration is the direction of the trajectory. Now, since the object is slowing down, the velocity won't be changed because the velocity will indicate the direction of motion. We are assuming here that the object is still moving in the clockwise direction, but this time it's slowing down. The velocity will remain the same at different points. The centripetal acceleration will remain the same, but this time the tangential acceleration will be acting in such a way that it will reduce the speed. And this is applicable if the acceleration is in opposite direction to the velocity. So it will be aligned tangent to the path at this point, but in opposite direction to reduce the speed. When the object moves to this location, then the velocity is downward and the acceleration is upward. In this location, the velocity is to the left and the acceleration to the right. And in this point, the velocity is up and the acceleration is down to kill or to destroy the velocity vector, which means, in other words, it will slow down the object. And can be done only and only if the tangential acceleration is opposite in direction to the velocity, because again, the tangential acceleration is responsible for the change in the speed. Now, using the same graphical method to determine the direction of the acceleration, now the direction of the acceleration will represent the diagonal of the rectangular shape uh, made by AC and AT vectors. And this is actually the direction of the A. And in this case, the direction will be to the left, and here up to the right, and here down to the right. Now, a 1,600 kilogram car is traveling over a hill that has a radius of curvature of 25 meters. The car is slowing down as it goes over the hill. It slows down at a constant rate of 25 meters per second to speed of 10 meters per second over distance 50 meters, ending at the top of the hill. So let me make a small picture for the situation. So the hill is considered to be half a circular path. So the car will enter the hill at this point with a speed equals 25 meters per second, and it will reduce its speed during the distance. So this is the distance here, which is 50 meters, until it reaches the top of the hill with a speed 10 meters per second. Now, here we are looking for finding the net acceleration of the car, but at the top of the hill. Now, to find the acceleration, we will need the two components of the acceleration. Remember that the acceleration is associated in circular motion with the centripetal acceleration and the tangential acceleration. But since we are looking for the net, it means the magnitude. In other words, I need to find the square root of AC squared plus AT squared. So let's find out the centripetal acceleration, which is AC v squared over R. And we can consider this point, V is equal to 10 meters per second, because we are looking for the net acceleration of the car at the top of the hill. Now, the tangential acceleration can be written as AT equals R times alpha. So let's start by finding the centripetal acceleration, which is equal to 10 squared root of 25. 10 is the speed at this point, and this is what we are looking for. And the radius is 25. Now then, the acceleration, centripetal acceleration at that point, the targeted point is 4 meters per second squared. Now, the tangential acceleration, actually, we have two different ways to find the tangential acceleration. We can use the angular kinematics to find the alpha, and then we plug inside this equation to find the tangential acceleration. And this is what I'm going to explain in a moment. However, we have different paths to find that tangential acceleration. Now, since the acceleration is constant, we are slowing down with the constant rate. Then the tangential acceleration is constant, and the type of motion here in this case is uniform varied motion. And we know that in uniform varied motion, we have set of equations that can be used here. V is equal V0 plus AT. Delta X is equal V0t plus half AT squared. Remember, this is the alpha. The acceleration here is the tangential acceleration. And V squared is equal V squared 0 plus 2a delta X. Now, no need for the fourth equation because it doesn't include the acceleration. Moreover, I'm not going to use this equation or that equation because the time is not given in that question. And the best choice will be this equation because this is the time-independent equation and it will help me to find the acceleration. Now, let's rearrange this equation to give us the acceleration or the tangential acceleration. So v squared minus v squared 0 is equal to a delta x. Remember, we are looking for the tangential acceleration, so we just move 2 and delta x to the other hand side and they become division. So v squared minus v squared 0 over 2 delta x is the acceleration. Now let's substitute. The v final is 10 squared minus the v initial is 25 squared, and the 2 times the distance traveled along this surface is 50 meters. And as a result, the answer will be uh, minus 5 point, I guess 25 meter per second squared. Okay, yes. Now, this is one of the methods, which is considered to be easier method to be followed. However, let me prove for you that even the second method is equivalent to this one. And the second method is based on the fact that AT is equal R alpha. Now, alpha can be calculated from the type of motion. Now, the type of motion here is uniform varied motion because the object is slowing down with constant rate. So we can use one of the equations given in the equation sheet for the angular kinematics. We're going to use again here the independent time equation, omega squared is equal to omega squared 0 plus 2 alpha delta theta. Now, our target is to find alpha. We move everything else to the other hand side. We start with the omega 0 squared. It becomes omega squared minus omega 0 squared equals to alpha delta theta. We move 2 and delta theta to the other hand side and becomes omega squared minus omega squared 0 over 2 delta theta. The problem here, we don't know what is the omega, and I cannot use these speeds. These are linear and not angular. The unit will prove that, or is it proving that? We know that the omega has a radian per second, and the theta has a unit of radian, and they are not given. We have learned how to transform theta or delta theta into distance, or in other words, we found a relationship between delta theta and the distance traveled and the omega with the linear speed. And we found that S is equal R delta theta, or you can consider it as theta. And for the omega, it's just V equals R omega. So by rearranging these two equations, we can find what will be the delta theta. It's S over R. And for the omega, it will be V over R. So let's use them in the previous equations. So I will replace omega with V over R. Since this is the omega final, I will use the V final. And for the omega initial, I will use the V initial. The same thing we will do for the delta theta. However, here, delta theta is S over R. So the answer is V over R to the power 2. The final speed over R, the initial speed over R to the power 2 over 2 S over R, the distance over R. Now let's substitute everything that we know. So the final speed, the initial speed, and the distance over the radius. And the answer will be alpha equals minus 0.21 radian per second squared. Remember, this is alpha, not the tangential acceleration. So as a final step, we just need to substitute this in alpha in this equation to get the tangential acceleration. And the tangential acceleration is equal to R alpha. So R25, alpha is 0.0. So the point is here. So 0.21. And the final answer is again minus 5.25 meter per second squared. Now we have the tangential acceleration. And this one is the same answer that we got when we solve it via the linear kinematics equations. Now, finally, the question was about finding the net acceleration or the magnitude of its acceleration. So we need to use the Pythagorean sum to find the net acceleration. And the net acceleration is equal to the centripetal squared, the tangential squared under the square root, and the final answer will be 6.6 meter per second squared. This is the magnitude of the acceleration. Now, unbanked curve. Now, what do I mean by unbanked curve? It's simply a curve or term that lies flat on the ground. So like this. So we have a flat surface, but the path here is a circular. So this is the unbanked curve. The vehicles on a horizontal circular unbanked curve are in a circular motion. Now, what keeps the vehicles in circular motion and attached to the circular trajectory is the static friction between the tires and the road and should be equated by mv squared over r. So this scenario we have studied in the previous session, and we found that the FF is equal mv squared over r. Now, although the car is in motion, but there is no relative motion along the radial direction, then for this is a static friction and not kinetic friction. What I mean by that, the friction is acting inward, and this is what we have learned from the previous session. And with respect to this axis, we call it usually the radial axis because it's toward the radius and passes through the center of the circular path. Now, the thing is, there is no any motion along this path. The object will maintain the same. There is no shifting up or down, inward or outward. So for this direction, the kind of the type of the friction here is a static friction because there is no relative motion along this direction. As the speed of the car v increases, then the term v squared over r increases. So as the speed increases, the whole term will increase, which means by maintaining the mass and the radius the same, which means the frictional force that needs to maintain the object in the circular path without sliding out, it should be bigger, it should be larger. Now, the unbound curves are engineered with a large radius, which means mv squared over r decreases, and this would require a less magnitude from the static friction to be equated by mv squared over r. So, as engineer, um, the radius here can be controlled. So, if we increase the radius, then the amount of frictional force required to maintain the object in the circular path will be less. So we can control the radius to control the frictional force, or let's say to control the object and maintain it in the same path. The curve in a stretch of a highway has a radius of 512 meter. The road is unbanked. The coefficient of static friction between the tires and the road is 0.7. What is the maximum speed here that the car can travel around the curve without skidding? Now, the forces acting on the car and during this motion are, we have the force of gravity, the first force acting on the object, the force of gravity, and the normal push because of the load, and finally the static friction, which is toward the center. Now we know that the friction here is promoted to be the centripetal force. Now let's apply Newton's second law. F net is equal to ma. Fg Fn plus Ff equals to ma. So this is the vectorial equation. Now we need to project. However, I'm not going to project along the x-axis and the y-axis. Instead of that, I will start to use different terms. So here, along this path, along this axis, this is the radial axis or the direction, the centripetal direction. So instead of saying this is the x-axis, this is the centripetal direction, and this one here is the vertical direction. So whenever you want to apply in circular motion the projection, you should mention these two directions. So let's apply the projection along the centripetal direction. Now, since this is the centripetal direction, then we don't use the Fnet in this classical way. We're going to promote it into the central version, centripetal version. So FC MAC. So let me write here, it's going to be FC equals MAC. Now the centripetal force here is only the friction, and the acceleration becomes here, in this case, centripetal acceleration, and it's written as v squared over r. Now Ff is equal mv squared over r, and we know that the Ff itself can be written as mu s over, sorry, Ff can be written as mu s multiplied by Fn, but this equation cannot be used unless we are at the verge of the motion. But since we are looking for the maximum speed, we cannot exceed this limit, because after that, what will happen to the motion? The object will start to move outward, and this is something not preferable. So we need to keep the object appears at rest along this axis, the centripetal direction. So approximately we are at the verge of the motion in the centripetal direction, which means we can use this equation in this particular situation. Now, remember that we are looking for the maximum speed. and the motion is at the verge of the motion, which means we can use directly Ff is equal us over Fn. Now, the thing is, the Fn is missing. We know the R, the mass, but the mu is given, but the Fn is not given, which means we will need to apply the projection along the vertical. Now, applying the projection along the vertical, Fn is equal to Fg, which means Fn in this case is equal mg. So now we can complete the equation. Mu s is times Fn is equal mu s times mg. Then we have, so we need to replace Fs or Ff with the mu s mg, and this is what we did. Now we can cancel mass with mass, and mu s times g is equal v squared over r. Remember that we are looking for v, so we move r to the other hand side, it becomes multiplication. So v squared equals mu s r g. Since we are looking for the speed and not the square of the speed, we just take the square root. And mu s r g is a very, very important relationship in unbanked curve. So this speed, not any speed, it's the maximum speed the object can move around the circle without skidding or moving outward in outward direction. And this speed here, in using this information, is 52.3 meter per second. Now the band curve. And what do I mean by band curve? Now, the band curve, it's simply a turn in which the driving surface is not horizontal like the previous case. So in the previous case, it was horizontal and circular around the circular path. Now, it's not horizontal anymore. It's still around the circular path, but it's not horizontal. Now, circular tracks are engineered to be banked. In a bank curve problem, the horizontal is taken to be the x-axis, while the vertical is the y-axis. So remember that we don't draw the x-axis parallel to the path or to the surface. We draw it in this way. Remember, the x-axis represents the centripetal direction and the y-axis represents the vertical direction. Now, how many forces involved in this case? Let's assume that the surface is a frictional surface. So we have the force of gravity acting vertically, and the normal push is acting with some angle with respect to the vertical. Now we found that this angle is equal to this angle. So always the normal push will make an angle equal to the angle of the ramp. And since we have, in addition to these two forces, we have the frictional force because the surface is rough, then we know that the frictional force is acting parallel to the road. So it will be acting in this way. Also, the frictional force will make an angle theta with respect to the x-axis. So theta here and theta there. Now, the centripetal force, it consists of the two components from the Fn and Ff. We know that the Ff can be decomposed into two components, the Fx, and for the normal push, we have another two components. One of them is the Fnx. So this is the Fny, and here we have the Fn, or sorry, not the Fn, the Ffy. So what did I do? I just decomposed the FF into two components, one of them along x-axis and the other one along y-axis, and I repeat the same thing for the normal push. Now these two components here, since they are inward toward the center, then this will be promoted to form the centripetal force. Now these components, in addition to friction, will help to equate the term mv squared over r. Note that for motion along a ramp, the x-axis is taken to be along the ramp. And let's take an example. For a car to safely negotiate in a curve of radius 25 meter at a speed of 30 meter per second in icy condition. When I say icy condition, I mean by that no friction. So I'm not going to involve my friction in the friction in my calculation. What banking angle would be required? So we are looking for this angle. This angle will control the stability of the car in the radial direction or in the centripetal direction. Now, what will be the angle needs in this case? Now, the forces acting on the car are, we have the pull of gravity acting downward, the normal push will be perpendicular to the surface, so it will be in this direction. There is no any friction here, so I'm not going to involve the friction. However, if I have friction, then the friction will be parallel to the path, like this, the normal push and the gravity. But here, in this case, we're going to ignore the friction. Now let's apply Newton's second law to find this angle. Apply Newton's second law. If net is equal ma, we have actually only two forces, F g and Fn, equals ma. Now we apply the projection along the centripetal direction. And along the centripetal direction, the Fn can be decomposed into two components, one of them along the vertical. So this is Fn since the angle with respect to the y-axis. Then, um, okay, so the angle is with respect to the y-axis here. Then this is the F cosine theta. And for the second component, which is along the x-axis, it will be Fn sine theta. So Fn sine theta, it should be the centripetal force. Remember, in the centripetal direction in circular motion, we apply this formula. And we know AC itself, it's equal to V squared over R. Now, this is the first equation. We need to find theta. However, we don't know what is the Fn, which means we will need another equation because we have now two unknowns. We need to have a second equation in order to solve for theta. Now, the second equation will be derived from the vertical. Now, along the vertical, the FG is balanced with the Fn cosine theta. So Fn cosine theta equals to the FG, which means Fn is cosine theta is equal to mg. This is the second equation. Now we have give the birth of two linear equations. We can now solve them simultaneously. We have different methods to solve them. We can substitute one of them into the other, but the easiest way to solve them simultaneously is by dividing 1 over 2. So we divide equation 1 over 2. So I will write Fn cosine theta over the Fn cosine theta. So everything on the left-hand side should be divided, and everything on the right-hand side should be divided. This is a very promising method to solve the problem or to solve the equations, system of two equations. Now, we cancel Fn with Fn. We know that the sine over cosine, actually it represents the tangent. So we have tangent here. Now, m with m cancelled out, v squared over r over g, we can press the r to the denominator, so we can write v squared. After pressing r, it becomes in the denominator and g next to it. So the tangent is equal v squared over rg. Now we substitute to find the tangent theta. So 13 squared, 25, 9.81. I will consider the gravity to be 9.81. And the radius at 25, it's given there. This is the radius of the path. And 13, the speed is given from here. Notice that the angle is independent of the mass of the vehicle. Now, this number here represents the tangent angle and not the angle itself. To find the angle, we just take the tangent inverse of 0.689, and the answer will be 34.57 degree is the angle of the banking. So let's practice. A car is traveling clockwise, so this is the direction of motion, around a circular racetrack of a radius 1440 meter. When the car is at the northernmost point on the circle, as shown above, it has a speed. So particularly at this point, the speed at this point, exactly at this point, is 36 meter per second, and is slowing down at a rate 1.2 meter per second squared. So we have an acceleration with this given value at this particular point. This kind of acceleration, since it's changing the speed, then this is tangential acceleration. What is the magnitude of the acceleration of the car? To find the magnitude of the acceleration, we will need the two components, AC squared plus AT squared. Now we have the AT, it's given in the question. We still need the AC to complete the picture. So V squared over R, the V is given by 36 squared, and R is given by 440. Now, for this one, the answer will be 0.9 meter per second squared. Now, to find the magnitude, we will need the two components, the 0.9 squared and the tangential component plus 1.2 squared. And the final answer will be 1.5 meter per second squared. So the correct answer will be D. On a level horizontal table, a toy race car of a mass capital M moves with a constant speed V around a flat circular racetrack of radius R. The car is now going around a bank curve as shown in the figure above, the band curve is higher toward the outside of the circular turn. The car can now travel at a higher speed without sliding because the band curve. So do you think that the band curve will decrease or increase the coefficient of friction? Actually, this is not true because the band curve has nothing to do with the coefficient. The coefficient is more related to the two surfaces that making the contact. So the surface of the car and the surface of the path. Since there is no any changes in the car made to the car or to the path, uh, at least in the material, then the angle or the speed won't be affected. So it's not true. Increase the momentum. Actually, the momentum is related to mass and the speed, and this has nothing to do with the angle. Allows the component of the normal force to point toward the center of the track, and this is correct because if we draw the vertical axis and the centripetal axis, then we know that the normal push will have two components, and one of them will be pointing toward the centripetal direction. And this is the reason why the object will keep moving in circular path. So the correct answer will be C. Why it's not D or E? Because the gravity, both of them are talking about the gravity, and the gravity has nothing to do with them because gravity is completely aligned with the vertical axis and it won't affect anything with acting on the centripetal direction. So gravity has nothing to do with this kind of problem. On a level horizontal table, a toy race car of a mass m moves with a constant speed around the flat circular race of radius r. Which of the following best represent the minimum coefficient of the static friction required for the race car to continue follow the circular path shown? So actually, we know in this particular case, the forces acting here are three forces. So this is not the situation where we have a band curve. This is unband curve. The normal push is acting up, the gravity is acting down, and the frictional force is inward toward the center. So I will use it in this way. It's fine. So from the side view, for example, if you want me to write it or to draw it in a better way, let's assume this is the circular path, and here our car. The friction is acting toward the center. The normal push is like this, and the gravity is like that. Now applying Newton's second law, F net is equal ma. Now we have only three forces acting here, so Fm plus Fg plus Ff, sorry, equals ma. Now first we apply the projection along the centripetal acceleration. Then Fc is equal mac. Only Ff is promoted to be the Fc because it's toward the center, and AC can be written as V squared over R. Now Ff, since we need to find the minimum coefficient, the minimum coefficient means we are at the verge of the motion. So we can write Ff to be Fn times mu s, static friction, mv squared over r. Now Fn is missing here, so we can find it via the vertical axis. Fn is parallel with the Fg, and Fn is equal mg. So let's substitute it back in this equation. So mu s mg equals mv squared over r. Remember, we are interested in finding mu s. Mass with mass cancelled out. We move g to the other hand side, it becomes division because now it's multiplication. And the mu s is written as v squared over gr. This is the minimum value of mu s that keep the object in the circular path. And the correct answer would be, for sure, it's going to be D. Now, a particle of mass m moves counterclockwise, so the direction of motion in this way. This is the counterclockwise direction around the horizontal circle of radius r as shown above. The angular speed of the particle is given by, so it's equation of time, omega t is equal pt, where b is positive constant and t greater or equal to 0. Which of the following best describes the acceleration vector for the particle at a moment shown in the diagram? So at this moment, what will be the direction of the acceleration here in this case? First of all, we can immediately say that we have centripetal acceleration to find the direction, because to find the direction of acceleration, we'll need the two components, the centripetal acceleration and the tangential acceleration. The centripetal acceleration, particularly at this point, will be toward the center. We still need to determine the direction of the tangential acceleration. Now, the tangential acceleration It can be zero or it can be positive or even negative. Now, the direction of the velocity is in this direction. So if the tangential acceleration is zero, no need to add the tangential acceleration, and the direction of the acceleration itself, it will be the same as the direction of the centripetal acceleration. In case the tangential is zero, how we can know if the tangential is zero or the tangential is constant or even the tangential is variable? So we have three options, or let's say possibilities. Now, in case the tangential is constant, then it can be written in terms of just a number. Let's call it A or B. If the tangential is zero, then the answer is zero. So the tangential is zero. If the tangential is variable, then the tangential will be written in terms, for example, BT. Now, we have different ways to do that. For example, we know that the tangential acceleration is directly linked to the angular acceleration. So we know that AT is equal to R alpha. And alpha is the derivative of theta, or sorry, not theta, it's the derivative of omega over time. We have the omega, let's apply the derivative bt. What is the derivative of bt? So this is linear equation. We know that the derivative of linear will be constant. So it's going to be b, which is constant. Now plug in b here, and the tangential will be r times b. R is constant, b is constant, so the whole term here is constant, which means the AT is constant as well. And the AT is constant, and it's going to be in the positive direction because the sign here is positive. So the direction will be, within the positive direction, and we know that the positive direction will be always the clockwise, the counterclockwise direction. We have defined in previous lessons that the counterclockwise direction is considered to be the positive. So since the AT or the tangential acceleration is positive, then the direction will be within the counterclockwise, and the counterclockwise state that the AT in this direction and the AC in this direction. So the direction of the acceleration will be to the left and toward the bottom of the page. And this can be found in D. In D, it has components directed toward the right, sorry, toward the left, not to the right. So it's not D. It's going to be E because it should be toward the left. This is the left. And the other component will be to the bottom of the page. Okay, and that's it for today's lesson on 10.10 or 2.10 circular motion part 3. Thank you for joining me. See you next time.